Okay, welcome back, everyone. Today's topic with Gord is on heat pumps, basically an overview, or he's going to talk about the fundamentals. Again, Gord, please feel free to take it away.
Thanks, Claude. I really appreciate that. And this is a topic that's, boy, it's really taken off in the last year and a half, 2 years. I've been doing a lot of training with utilities, with builders, with HVAC contractors, general renovators. And the reason for that, I guess, highlighted for that is the tremendous efficiency of heat pumps and the recognition of heat pumps in the newest government incentives. That is, for as long as I can remember being in business 30, 35 years, Claude, I'm sure you're the same. Every federal government program, every provincial program always provided funding for people to go to higher efficiency gas or oil or whatever furnace you were using, fuel fired equipment you were using. Now the incentives are reserved for those who are switching to all electric heat pump based systems. And yeah, the folks on this call has probably heard this. And so we really need to think about the advantage of heat pumps and therefore know the fundamentals of those heat pumps. So that's kind of the premise for this session. But it's been interesting to me, the number of training courses that I've done, and still the, not skepticism, but the sort of sideways glance as to whether heat pumps can really work in Canada or not. So that's why we wanted to do this session. In terms of what I thought we would cover over the next 45 minutes or so is how heat pumps differ from other types of heating systems that we're used to, some of the types of heat pump systems that are available to us, the advantages of those heat pumps, but then some of the important things to consider when applying heat pumps in new or existing buildings or houses. And then I want to touch base just a little bit on hybrid systems as well. And so let's remind ourselves that, we have a long history of fuel-fired appliances in houses, from oil to gas and propane. And we even had electric furnaces. And Claude, I'll ask you, hopefully you're still there online. In your house, what's the heating system of choice in your house?
I have a high efficiency forced air gas fired furnace.
Wonderful. And that's high efficiency, and that would be, we typically would say high efficiency is anything in the range of 90%. And those appliances were, I would say, became popular in the 1990s. Before that, in the 1960s, we had appliances there you see on the left that were about 60% efficient. I always like to say it this way: for every dollar of gas or oil you bought, you got about 60 cents worth of energy or heat into your house. 40% of it went out the chimney, went out the side wall, or went out the side jacket of the units. They were only 60% efficient. And then in the 80s, they would develop systems that were more efficient, about 80%. So every dollar of gas you bought or oil, you got 80 cents worth of heat. And then, as I say, in the 90s, we got to about 90%. And now the national code is at minimum 95%. You can't even sell a furnace unless it's 95% efficient. That's gas or propane. Now, oil kind of got stuck down around that 80%. It's almost impossible. It's very difficult. There are a couple, very difficult because of the condensation issues, the corrosion, and so on. Very difficult to make an oil burner more than about 80, 85, 86%. There are a few out there that are 90, 94, but they are pretty finicky, and would be my opinion, I guess. Maybe the manufacturers would disagree. Of interest, perhaps, though, is electric furnaces. They were 100% efficient. For every dollar of electricity you buy, you got $1 worth of heat. Now, the price of that fuel, electricity, historically has been way more expensive than, say, natural gas. It's been roughly the same cost as propane or oil, depending on where and when you bought your oil or propane. But so electricity was an efficient fuel, 100% efficient, but it wasn't as cost effective, say, versus gas or propane, because the fuel itself was more expensive. But that's kind of been the history, is to try to take a nice, reliable product like a gas furnace and try to use that natural gas as efficiently as possible. And we got ourselves up to, say, 96%, 98, I think, is the the best you can buy in these days. And there, just as a little example, a graphic of a traditional gas furnace. Inside the box, you see there on the left, sort of top left of the picture, had a primary heat exchanger, and then it had a secondary heat exchanger. That was the advent, I would say, of the high efficiency. It used to be just one heat exchanger. Now within this, two heat exchangers. And the concept was on the top right, you would take combustion air in, you would burn it inside a sealed chamber. Inside the heat exchanger, there would be the hot combusted gases, and flowing across that on the other side of that heat exchanger would have been air from the house. And the air from the house would have come in at, say, 20 degrees Celsius from the house. By the time it exited up the top of the furnace, it was increased to, say, 45 degrees Celsius, maybe 50 degrees Celsius on an oil furnace. And the products of combustion, now they've given up all their heat, they're full of condensation. We would use down the bottom right an induced fan motor to exhaust the products of combustion outside. So we had a sidewall vent. So we had two vents on the outside. We have a combustion air inlet and we have a combustion exhaust vent to the outside. And it was these new appliances are sealed combustion, they're direct vent, very safe, very reliable. You got a nice warm air feeling coming off of it. The two other bullets, the last two bullets, refer to the duct pressures that these guys could accommodate. New furnaces are able to accommodate more ductwork, better filters because of higher external static pressure. That's what ESP stands for, external static pressure. So not only did they improve their efficiency in terms of how they burn gas, they also improved the way they distributed air and filtration of air and so on. So really nice, advantageous, but nonetheless still only 95, 96% efficient and still using a fossil fuel based product. So that's what's of interest. I do want you to note that just again, the 20 degrees Celsius coming in, the 45 degrees Celsius air going out. So that was traditional gas furnace. And then some will be familiar with traditional air conditioning. So this is a refrigerant-based device that on the outdoor unit, notice the outdoor unit there on that house, it takes in outside air, say at 30 degrees Celsius, hot summer's day, extracts heat from the air, from the refrigerant, and actually expels heat to the outside. An air conditioner actually makes the outside of the building warmer. It heats up Mother Earth. On the inside, you'll notice the refrigerant is used to absorb that heat from the house. So the air comes in, say, the return of the furnace at 23 degrees Celsius and comes out the top of the air conditioner at 10 degrees Celsius. It's taken out roughly 13 to 15 degrees Celsius of heat, and it's taken that heat and it's transferred it to the outside. That's the word I want us to start thinking about. It's not cooling the air particularly, it's simply taking heat from inside the house and transferring it to outside the house. Now notice the temperature difference between the return air, 23 degrees Celsius, and 10 degrees Celsius. That's only a 13 degrees Celsius drop. You noticed in the furnace, it came in at 20, went out at 45. That was a 25-degree increase in temperature. And so typically air conditioners, for the same number of BTUs of energy, need more air. You need more air to cool than you need to heat. And that's only the sensible heat load. Also in air conditioners are also dehumidifying the air. How are they dehumidifying the air? As that temperature drops to 10 degrees Celsius, it actually condenses the water out of the air, and that condensation runs down the drain. So cooling systems, traditional air conditioning systems, transfer heat from inside the house to outside, and they also remove moisture. And the reason I wanted to show air conditioning, not all communities would have air conditioning, but I wanted to just show you an air conditioner because an air conditioner is actually a heat pump. It is a device that pumps heat from inside to outside. And when we go to the idea of a heat pump is simply a device that's moving heat from one place to another. An air conditioner moves hot air from inside the house to outside the house in the summer. A heat pump has a reversing valve to it. All it does is reverse that process of an air conditioner. So a heat pump is effectively an air conditioner that has a reversing valve in it. but it has this ability in the winter time to take heat from the outdoor air and deliver it back to the house. In the summer, it took the heat out. In the winter, it's going to bring the heat in. And there's generically, I will say, 3 types of heat pumps that are out there. Most will be familiar with the term ground source or water source heat pumps that are using loops in the ground. The ground stays at a relatively constant temperature all across North America at roughly, well, a little colder, obviously, the northern or farther north you go. But even at 8 feet down, the temperatures, even in the far north, are in the order of 5 to 10 degrees Celsius. That's a very stable amount of energy or heat, and we simply use loops in the ground to extract that heat and deliver it to the house, or in the case of air conditioning, we reverse it in the summertime and get cooling. What we're going to talk most about today is in the middle, is the air source heat pump, where it's taking heat from the air outside, extracting it, if you will, and pumping it inside, transferring heat from one place to another. The key here is we're not making new heat. We're not burning a blue flame. We're not burning oil. We're simply transferring heat from one place to the other. In terms of air source heat pumps, there's sort of 2 generic versions. There's ducted, which is in the middle, looks like a traditional furnace or air conditioner, it's ducted. Or you see now more and more common ductless systems, where on that picture there on the inside, the head, what we call a head above the window, that's just a non-ducted system that just heats and cools one space or one room. But they're same technology, transferring heat from inside to outside. So an air source heat pump, it's, as I mentioned, is simply an air conditioner with a reversing valve. It has an outdoor unit that extracts heat from outside. It does work harder as it gets colder because there's not as much energy in the outside air. And this is really the crux of the conversation for today. If I said to you, is there any heat in the outside air? Well, if it's minus 10 degrees Celsius, that seems pretty cold. But in fact, minus 20 degrees Celsius is even colder. So what a heat pump is doing on the outside is it's taking in minus 10 degrees Celsius air, extracting heat from it, and expelling that air back to the outside. It's making outside colder. So in the winter, heat pumps are making the outside colder, but making the inside warmer. They're simply transferring that 10 degrees Celsius worth of heat back to the inside. It warms up the incoming air in the house by from say 20 degrees Celsius up to 30 to 40 degrees Celsius. It's adding that heat. And as it gets colder outside, let's say it's minus 20 out, well, there's still heat in that outside air, but not as much. So the heat pump has to work harder. But what's really interesting to understand is its coefficient of performance, its efficiency, if you will, its COP is typically 3 to 4. Let me say it in a non-technical way. For every dollar of electricity it takes to run the heat pump, the compressor on the outside, you get $3 to $4 worth of heat on the inside of the building. Isn't that interesting? A gas furnace is 95, 98% efficient. Heat pumps are 300 to 400% efficient. Now, we don't use the word efficiency. We use this term, this technical term, coefficient of performance, and it's 3 to 4. Another term you'll sometimes hear is the heating system performance factor, an HSPF. And it's a measure of the BTUs out versus the watts in. Not sure exactly why we use HSPF. I like COP because it seems simpler to me. But a COP of 1 would be an HSPF of roughly 3.1. And so an HPS of 10, for example, would be a COP of 3. So hopefully that doesn't confuse folks on the call. The key learning here is heat pumps, when they're most efficient, have a COP of 3 to 4, which means for every dollar of energy you spend to run the pump, you get $3 to $4 worth of heat coming back in the house. And many would say, but electricity is expensive. Yes, electricity is more expensive than some other fuels, but what we do know is we need that efficiency. We have, in most parts of the country, we have really clean electrical grids, hydropower, nuclear power. So from an environmental standpoint, it's very useful. One, to use less energy, units of energy. as a heat pump is doing, and then to use an electrical based system rather than a fossil fuel. We'd rather not be burning fossil fuels in houses anymore. So that's why this is becoming so of such interest and so compelling, is to move us towards heat pumps. And the other nice part is when you think about it, if you're making your own electricity, let's say you had a wind generator or solar panels, well, now your electricity is free. And the end game, the goal would be to say is, let's move houses towards electric based systems, and then let's generate our own energy locally or nationally on a grid level to think about really clean electrical sources. And lastly, we know, because of our national commitments, international commitments to greenhouse gas reductions, we know there's going to be carbon tax or carbon incentives to move away from fossil fuels. That is, the price of natural gas and oil and propane are going to go up rather dramatically over the next 10 years. And the price of electricity will stay, we presume, or we think will stay pretty flat. So right now the price of electricity may be high, but in future you might say, I really want to use a device that's 300% efficient. And even if that fuel is, more expensive, I could generate my own using solar or wind or other sources, even localized hydro. So that's really the essence of heat pumps as we move through this. And so heat pump features, just to go over it again, just to give you a couple of thoughts. It has an indoor and an outdoor unit or coil. You saw the outdoor unit looks like an air conditioner, an outdoor and indoor. So therefore inside it looks like a traditional furnace. And all really it has is this automatic reversing valve for summer and winter. And it transfers energy between indoors and outdoors. And it always includes this closed loop refrigerant system. So it's the magic of refrigeration, much like in fact, your refrigerator is a heat pump, the thing that keeps our food preserved, our freezers and so on. Those are heat pumps. That's a refrigerant based system. The reason I mention that is, if you are going to have heat pumps in your community, they'd have to be serviced by a licensed, qualified refrigeration technology, a technologist or contractor. And that's something to think about, whether that expertise is available to you either locally or in your community. But also understand that there's been lots of these installed. This isn't a new device. There's over 7,000 heat pump systems installed in Canadian houses, and they are getting more and more common. Every HVAC contractor, every HVAC wholesaler, heating, ventilation, air conditioning contractors, they're now doing these devices. And you do need to know that they're compatible with a variety of supplemental heating sources, which I'll show you in a bit. That is, if you don't want to rely 100% on the heat pump, there are backup or supplementary heating systems that can be used. But they could be all electric. If you wanted to get rid of fossil fuels entirely in your houses, you could be all electric systems running off that heat pump, and they're compatible with a variety of thermostats. The thermostats do need to work differently. That is, you need a heat pump compatible thermostat because it controls slightly differently than a traditional furnace. So most thermostats already include the ability to run heat pumps, but you'd want to check on that as you move through it. And I'll just mention that many of you might be familiar with geothermal systems. These are ones that are using the ground, the constant temperature in the ground for the heat source. So that's common in some of your community buildings. Makes a lot of sense. The cost of running the loops in the ground is typically too expensive for individual houses, but to do a collection of houses, say as a district heat, or say a school, or as say administration building with geothermal that has higher loads, then it definitely could be justified. And ground source heat pumps are typically more efficient. Why? Because they're seeing a very constant ground temperature. As you noted earlier, the temperature of the air changes, gets colder and colder, and heat pump has to work harder. With ground source, you're actually seeing the same ground temperature summer and winter, so you have a very constant source of heat, and so the heat pump tends to be more efficient. It can be sized more accurately, and it's more efficient. So that's geothermal. Again, as I move through this, just to constantly remind you that we have to get the heat pumps. We just need that efficiency. We need that energy savings. Notice that bottom bullet. They save about 10 gigajoules of energy per year in a typical home. And we need that energy performance for two reasons. One, to lower costs for occupants, and two, to meet our greenhouse gas reductions targets as a country, as well, frankly, as an international community. All of us need to think about getting rid of or using this much more efficient source of energy, if you will. And as I was kind of alluding to, there's lots of options. There are new, on the left, heat pump water heaters. In the middle there's multi-terminal options that you could imagine for public buildings or larger houses. You can even use hybrid dual fuel based systems, so that if I still want to have some gas or propane or oil or wood, there are ways of combining those two technologies we'll chat about. And there are some new air to water heat pumps coming, so that if you wanted to heat hot water in your house, in-floor heating and so on, there are air to water heat pumps now available. So lots of options, and some new ones on the way as well. So here's a little example of a ductless mini split on the left-hand side there, that one outdoor unit and a cassette or a wall-mounted unit to heat your house, or that Fujitsu unit that you see there could also supply an air handler or a hot water tank as well. So lots of options out there to imagine in your houses. And these ductless systems are a really good option, specifically in existing houses. If you've got houses in your community that are electric baseboard, for example, or maybe just a one wood stove with some electric baseboards, heat pumps can be installed without ductwork, and you would have, as I mentioned, one outdoor unit, but then you could have a bottom right, you could see a wall-mounted head, for example, in a bedroom or the main living, let's say in a bedroom area, or you could have on the top left, you could have a cassette that runs in the ceiling, say, of the kitchen and family room area. The one on the right is a little mini ducted unit that could go into a couple of bedrooms. So this is a really good option, relatively easy to retrofit into existing houses that don't have forced air systems. So that's pretty useful. But I do need to acknowledge, and we need to be conscious of that fact, that there are some challenges to heat pumps, that it's not just a change it out quickly, change it out. We have to think about what the differences would be between current heating systems and heat pump, these refrigerant-based heat pump systems. And we do need to acknowledge, and you're going to hear this from community members or from HVAC contractors, heating ventilation contractors. They're going to say to you, heat pumps didn't used to work in Canada. And that was in fact true. 20 years ago, they were incredibly inefficient. They were not designed for our cold weather. They were unreliable in cold weather. They just froze up, as you can see here. They were really difficult to size in Canada for heating and cooling, mainly because our houses were really pretty inefficient and we had very large heating loads. So it was really difficult to size them. They were traditionally poorly installed. They weren't well understood. They were noisy. They did require much larger duct sizing because they have lower discharge temperatures. And so that created some challenges. But what's nice to know is things have changed. Even since 1990, for example, even any house built in your community since 1990, and any new modern house, they have much smaller heating loads. So the heat pumps don't need to be as big as they used to be. Our ductwork systems are better, so we don't have to worry as much about if we've got forced air systems. And the equipment has changed, and now we have equipment coming from all over the world that is in fact more efficient and designed specifically for cold climates. That's what we need to understand, specifically for cold climates. And when we assess, and there's a really good tool from CanMat, Natural Resources Canada, that you see it there on the left, to be able to determine whether you could put a heat pump into an existing house or a new house. It's a lovely guide, quite a well thought out guide. And what we ask, of course, is to figure out what is the size that's needed for heating or cooling. And we have to determine the ductwork. As I say, in older houses, very old houses, the ductwork may not be big enough. In some cases, we wouldn't need to use ductwork at all, but we'd need to look at the ductwork. And we'd also need to look and see if we need backup heat. That is, we may not want to size the heat pump for the coldest day of the year. There's a reason to think about sizing the heat pump for the majority of the winter, but on the very coldest of days, maybe putting in a little supplemental heat or backup heat. It allows you to make the heat pump smaller and therefore more cost effective. So don't discount the interest and say, well, I got to do it all in heat pump. No, there's not a problem doing a little bit of backup. These devices are electrically based, so we have to make sure we have the appropriate service panel size. But typically in your communities, that's not typically an issue. Many of you, the houses would have been sized for electric heat anyway, and these devices use less electricity than, say, the collection of baseboard heaters that might be in your houses. But it is something that needs to be checked. And then, of course, we have to think about access to outside. We are going to have to run refrigerant lines. So think about multi-units, maybe little row houses, and is there a place to put this outdoor unit? So we need somebody in the community who's able to take this guide, go into existing houses and say, could we do this in these houses? And these are the items that they would be looking at. And there is this great guide available to you. And then the big challenge is to avoid, to get the sizing right, to make sure that we have not oversizing from an expense point of view or undersized that people might be cold. And what the first thing we would say, and I'll talk about it here a bit more, is to do a proper heat loss. That's what HL stands for, and heat gain. And in many of your communities, you would say, well, air conditioning is less important to us because you're in milder climates, in summer milder climates. But still, you'd want to do a quick check just to make sure that there was a good match between the heat loss and the heat gain. And there is a standard for this called CSA F280. And the reason I mention that is HVAC contractors, heating contractors, should be trained, and you would ask them, if you're working with them, could you make sure you do a proper heat loss and heat gain for this house to find the right spot where we're going to do this? And again, Natural Resources Canada has this heat pump sizing tool that'll help you size the piece of equipment based on your heat loss, heat gain, and then determine, is the ductwork big enough? And sometimes you need a variable or two-stage heat pumps to avoid overcooling, for example, in air conditioning mode. But typically, we're going to try to size this so you don't necessarily need variable speed equipment. So we're just going to talk about that sizing just a little bit more. There on the right-hand side is just the front cover of that heat loss, heat gain standard. It's been around since 2012. And here's what happens. When they do the heat loss, heat gain, you basically measure the house, the walls, the floors, the ceiling, and you calculate the conduction heat flow through those walls, those floors, their ceilings. It doesn't take a lot of work. We simply need to know what's your coldest day in winter, what's your warmest day in summer, and we do a calculation. To do a heat loss, heat gain calculation on a house, a typical house, is about an hour to do. There's all kinds of software programs available that help with this. What we would say is just don't use old rules of thumb. Just go ahead and do a proper heat loss, heat gain on a house. Takes about an hour. Measure the house, and maybe you already have the sets of plans of the house. Measure the windows, because that's the next thing. It also takes into account the amount of heat flow, both summer and winter, through the glass of the house. So we do that. And then lastly, there's an element associated with air leakage and ventilation. So we think about the conduction losses through the walls, floors, and ceilings. We think about the radiant flow through the glass, and we think about air leakage and ventilation. And as I say, HVAC contractors can do this work. It's fairly easy to learn. There's training programs available from the Heating, Refrigeration, Air Conditioning Institute. If you had community members who wanted to learn how to do this, I think it's a 3-day training course. I believe it's now offered online. So somebody in your community could be qualified to do these heat loss, heat gains, or perhaps there is a heating contractor in your area that could do these as well. So that's getting the size right is important. And when you're doing that, then you'd want to make sure that they knew the insulation levels in the walls or the attic. Look at the thickness of the wall, look at the insulation in the attic. Also understand the windows, certainly in new construction, using the window ratings, proper window ratings. In existing houses, it's possible to measure the performance of windows. So if you don't know what the performance of the windows are, there's ways of determining that. And then house air leakage. And many of you on this call will know what a blower door test is, an air tightness test. It would be nice to know very important to know the air tightness test. And the good news is the energy efficiency programs like the Canada Greener Homes program, the Eco Energy programs. I have been advocating blower door testing for years. I've been on many of your communities and done blower door testing. I know that many of you have probably had experience with doing testing. The equipment is available typically in all regions of the country. And so either somebody in your community could be qualified to do those, or again, there would be energy advisors available to do that, because it would be nice to know. That's the important information that we give to contractors. Thought I'd show you a quick example of just how much heat loss can vary. If I take a typical 1,200 square foot house built to the current National Building Code, you can see where the energy goes in the pie chart. 30% to infiltration, because houses, unless you're testing, aren't necessarily airtight. But a typical house, and of course I shouldn't do this because if you write down this number, you're gonna say, well, my heat loss is, no, I'd need to know for Edmonton, I'd need to know for Ontario, I'd need to know for the Maritimes. Each region, of course, has different temperatures. Heat loss, heat gain is going to be different, but I'm going to use as a typical. I did this for a 1,200 square foot house near Ottawa, Canada, and the heat loss of that house was 38,000 BTUs per hour. 38,000 BTUs. And I need to immediately convert that to tons, because heat pumps are done by tonnages. And 38,000 BTUs is just over 3 tons. That is, there's 12,000 BTUs per ton. 12,000 BTUs equals 1 ton. So 38,000 BTUs, 36,000 would be 3 tons. So you can see we're just over 3 tons. So to heat this house in the dead of winter, I would need a 3-ton heat pump. But if the house was built to the newest standards, what's called the Net Zero Energy Ready standard, that house would only have a heat loss of 18,000 BTUs. Now you say, well, now the heat pump 18,000 BTUs, that's only a ton and a half. So instead of putting in a 3-ton heat pump, the house on the right only needs a ton and a half heat pump. That's obviously less expensive, less noisy, less to operate. So very powerful to think about if you're applying heat pumps, to know exactly how your house was built, or if you're applying it to new houses, make sure you build them energy efficiently. Or if you want to apply them to an older house in your community, then you would say, should we do some energy upgrades first? Should we add insulation in the attic? Should we do a blower door test and make the house tighter? Or maybe it's time to change the windows. Now the heat loss goes down and the heat pump can be smaller. And so heat pumps, the cost of heat pumps is very much related to the size of the heat pump. 1.5 tons is far less expensive than a 3-ton heat pump. Ductwork is smaller, so on and so on. So really good reasons to do a heat loss, heat gain, especially if you knew, and as I just told you, takes about an hour to do. It's certainly, with the proper software and the expertise is available. It can even be done remotely. Off a series of pictures and sketches, you can send that off to somebody like myself and say, hey, could you do a heat loss for us? We're here in north of Edmonton, or north of Northern Ontario. Here's our climate zone. Here's the city or town we're in. Could you do a heat loss, heat gain for us? So they can be done remotely, because we don't necessarily have to be at the house, as long as your eyes and ears for us to tell us what's there in the house. So just get that heat loss, heat gain done correctly. And I'll just sort of reiterate that one last time. This new CSA standard as of 2012 gives much better, much closer predictions of heating cooling loads. HRAI, the Heating, Refrigeration, Air Conditioning Institute, has what's called the RESD, which is the Residential Air System Design Manual. Sorry for all the acronyms, which provides guidance on duct sizing for both new and existing houses. So there's some really good guides out there that would help you determine A, what's the right size of heat pump, B, what's the right size of ductwork, how does it have to be distributed. And again, I'll mention this tool on the left, this really nice sizing guide. And then lastly, to remind yourself that there are really good new equipment options to provide more consistent capacities in cold weather. So I've got that one again, my apologies. And the next is, okay, how do I determine the right size? And here's the key. What we need to know is the capacity of the heat pump changes as the temperature gets colder outside. It's just the nature of heat pumps. It gets colder outside. They tend to reduce the capacity of that equipment reduces. So I have to figure out what is the capacity of the heat pump at different temperatures. So that's what the graph is showing you there on the right, is that red line is showing the reduction in capacity of the heat pump. This is a little more dramatic, but it shows you a 3-ton heat pump. We're in Fahrenheit here on the bottom of the graph. That's showing you the temperature. It's going from colder, 5 degrees, all the way up to 61 degrees. And you'll notice that the heat pump at 47 degrees, which is a very common rating point, the heat pump, now looking at the red diagonal line, if I follow that up and follow it across to the left-hand side, that heat pump has a capacity at 47 degrees of just over 30,000 BTUs. You notice the graph? But at 17 degrees Fahrenheit, it only has a capacity of 21,000 BTUs. So I would have to size it. I'd need to know the heat loss of the house, which is the blue line. And what is your coldest day? So if you get colder than, say, 17 degrees Celsius, Fahrenheit, many of you would, then you'd say, wow, that heat pump is only going to get me 21,000 BTUs. It's only working like a 2-ton heat pump. Remember, it has a 3-ton capacity at 47 degrees, but it only has a 2-ton capacity, just under 2 tons. 24,000 BTUs would be 2 tons at 17 degrees. Its capacity drops. Doesn't make it a bad appliance, just the nature of the beast. So you would say, I don't need 3 tons, I need 2 tons. If you're in a warmer climate, obviously, then you don't need to think about that as much. But here's a really nice piece. There are new cold climate heat pumps, and many of you, for many of your communities, the farther north you go, you're going to want this new variant, this new type of appliance, and you would simply specify a cold climate heat pump, what they call a CCHP, cold climate heat pump. And notice the normal heat pump, the standard heat pump, is that gray line. And notice from the right to the left, as it gets colder from 8 degrees Celsius down to -8, notice how its capacity dropped. Notice how the cold climate heat pump, the red line, maintains its performance all the way down to -18 degrees Celsius. And you go, we get colder than that. Yes, and there's cold climate heat pumps that will go even further than that. There's now cold climate heat pumps, and you'll notice even down at -13 Fahrenheit, -25 degrees Celsius. Some of you do get colder than that. Most of you would say, that's about us. Then you've only reduced the performance down to 78% from 100%. So you've only lost 22% of its performance. In other words, you'd have to oversize by about 22%. But the key is to work with manufacturers of the heat pumps and their representatives, and your contractor is going to install this, and understand, what is my climate zone? How cold do I get? It's not the coldest day ever, because we're going to put a little supplemental heat anyway. But in general, how cold do you get? Let's size the heat pump, cold climate heat pump, for your communities. And I'll say again, lots of new equipment available that now are able to work in very severe cold temperatures. And then remember, we're also going to do some backup as well. So we're not going to be in too bad a shape. So that's the cold climate. And I just wanted to show you here again in graph form, the the one on the top row, if you will, the X24, it loses its capacity. Its heating capacity is 26,000 BTUs at 8 degrees Celsius, only a ton and a half at -8 Celsius. And it doesn't even rate. This heat pump clearly at -15 doesn't even have a rated capacity. So that would be appliance you would say, I'm not buying that in Canada. That's not the one that's for me. I need, unless you're in lower mainland Vancouver, in that area, or the coastal regions, maybe you could go with that one. But many of you would say, no, I need a heat pump that actually gets me better performance. And notice this heat pump, the bottom one, the CC24 cold climate, maintains its heating capacity, 22,000 BTUs at 8 degrees Celsius, 22,000 BTUs at -8 degrees Celsius, 22,000 BTUs at -15 degrees Celsius. So This is the kind of appliance that you would say in colder climates, colder communities, you would say, I need these kinds of appliances that maintain their performance throughout the winter. And again, if it drops off on the very coldest of days, it's not as if they stop working, by the way. They continue to work, they just don't have the same capacity. So you may need some supplemental heat. I'm going to say that one last time. They still work at colder temperatures. They're just not as efficient or as high enough capacity that you might need for your house. So there's nothing wrong with thinking about supplemental heat. So I want to again reiterate in terms of our fundamentals, there's some tremendous advantages here. They're all electric, so I could start thinking about getting rid of spillage susceptible appliances in houses. I could, in fact, do an all electric version. You would say I said to you, you need supplemental heat. Yes, you could do supplemental electric heating if needed. They look like a traditional furnace and air conditioning system, and in fact, they provide air conditioning. So you don't need to change the layout of the ductwork, don't need to change the layout of the basement. If you're doing a ducted heat pump, they typically get installed in the same place where the furnace is now. And the newer devices have these variable fans and compressors, which means they have much lower power consumption, that efficiency I spoke of, 300 to 400%. And it's these variable speed fans and compressors that also allow this equipment to run in colder temperature. So you are going to be looking for variable speed because that's what works in cold temperatures. So tremendous advantages to that. And I'm going to say heat pumps are going to be standard, whether it's ground source in your community buildings or air source heat pumps in individual houses. You're going to see more and more interest in heat pumps, one from an energy efficiency standpoint, environmental benefits, and cost of operation. Heat pumps have tremendous advantage. They give you fuel flexibility. As I said, you can still run them. I'll show you here in a second the hybrid heating systems, but they're emission free. When the heat pump is running, they're not emitting any carbon dioxide into the atmosphere. That's very useful. They very clearly have the best of efficiencies. Keep that in mind. And they're a really good match to solar. If you're running solar in your communities, boy, now you're making your own electricity. Now that's a really good match to an electric-based system. Some like to call it free energy. That's kind of an interesting term, right? You're using the heat that's already in the outside air. You're using that heat to heat your house. They're incredibly quiet, which is pretty powerful. And they have this really good environmental payback. From an environmental standpoint, we'd like to get the heat pumps. You have to be cautioned, again, in your communities far north, to make sure that we're sizing correctly and have good refrigeration technology up there in your communities. Sometimes that's a challenge, right? Depending on, don't know who's on this particular, listening in on this particular call. I do understand that sometimes, depending on how remote your community is, may be more difficult to get these kinds of equipment up your way, and more importantly, to get folks who are qualified to install. And as a community, perhaps you take on that to get the training done. But I did mention, I just want to reiterate, if you already are running oil or gas furnaces, it's okay that you can add heat pumps to the top of, over top, much like an air conditioning coil. The heat pump sits on top of that furnace. In this case, the heat pump can't run when the furnace is running. So typically what you do is you have a switchover point based on the right-hand side there, based on the efficiency or based on the outside temperature or based on the cost of fuel. You would say, I'm going to run the heat pump as much as I can in mild climate or mild weather. And when it gets colder, I'm going to switch over to gas. That's a very common approach, whether it's gas or propane. So heat pump, 300% efficient, say when it's spring and fall. Today, it's about, in where I am in Cambridge, it's about 7 degrees Celsius. That's a really good day to be running a heat pump. But when it gets to -5, -10, I'm going to switch to my gas furnace. This is typically, it's not exactly what I have, but this is the way I run my house. I try to run the heat pump as much as possible in the mild weather and then switch to natural gas for the added heating capacity and for savings, cost savings, because the price of natural gas is still at this moment less expensive than the price of electricity. And as that changes, what's interesting about this is as the price of fuels change, you can change the thermostat settings. There are now thermostats that can adjust. They actually get to know the temperature of where the equipment runs best, and they can be connected to the cloud, and you can input what is the fuel prices, and it'll make a determinant of which is most cost effective and when. So kind of interesting. This is exactly the way I run my house. I have what's called a heat pump air handler. In this case, the heat pump coil is below the regular heating coil. And above my heat pump coil, I have a hot water coil. I run the hot water off of a gas boiler. So my gas boiler heats my hot water for my house, but it also provides supplemental heat for this heat pump. Now, that coil could be an electric resistance coil. So if you don't want to run fossil fuels into a house, oil, propane, and so on, you could use an electric resistance coil. What's really nice here is the heat pump can continue to run. So both the heat pump and the supplementary coil can run at the same time to give you the best efficiency, best capacity. In all of your communities, you're always going to need some sort of supplemental heat. And it could be one of a few things. It can be the hot water coil run off of fossil fuel, or it could be an electric resistance coil. So two different ways to get that done. And so this gets you really nice efficiency out of this. And they have these new, down at the bottom, 2 bullets, ECM fan motors that do a really nice job of minimizing electrical cost for these units. And the key to this one is both coils can operate at the same time. So depending on your community, and this is where, this was a fundamentals course. We can do more on this at another time, Claude, but this is the basics. I can run all electric heat pumps, or I can run dual fuel heat pumps. And there's a couple of different ways of doing those dual fuels. So here's an example of a gas furnace. It's called a Detson gas furnace. And the heat pump coil sits on the top of that. The outdoor condenser units there in the middle. They still have hot water backup. They're showing an HRV there on the side. So just some of the things that are involved in a house. Or as I mentioned, you could do all electric heat pump there on the left with multiple heads, really good choice, or hot water air handlers on the right-hand side. And I want to reiterate again that ductless supplementary systems are a great option in existing houses that don't have forced air. If you have houses in your community that are right now running off electric baseboard, one of the simplest things you could do to reduce energy costs for your community members is to run a heat pump. And you don't necessarily have to run the heat pump in the whole house. You could say, I'm just going to put in one head in a central area, let that central area still probably keep in the baseboards just for some supplemental heat. But the most of my heating is going to be done by this heat pump. And so high on the wall, in this case, ahead, there's cassettes you can put in the ceiling. This is a tremendous option that's being used both in First Nations communities and in places like Quebec and the Maritimes, where a lot of electric baseboard heated houses, they don't have ductwork. This gives you, I'm going to say, right off the chute, about a 30 to 50% reduction in electric bills to heat your houses by putting in the heat pump. It doesn't have to be sized to heat the whole house. It's sized typically to 2/3 of the heating loads, and it tries to heat 1 or 2 spaces within that house. It's very powerful. And so if I was to summarize, I would just say to you, hard to ignore an appliance that's 300% efficient. Heat pumps are going to become standard. Really need that efficiency. Second, remind yourself that they've become way more reliable in cold weather than before. So if anybody says to you, heat pumps, we tried them, they didn't work, that might have been true, but it's not true anymore. You can find heat pumps that will work in your cold climates. Again, they still may need supplemental heat, no problem, but you can run these. And there's more products and more options than ever before. Take the time to size them correctly. That extra hour, maybe it's 2, to properly size a heat pump. Get used to that, please, because we've seen way too many heat pumps undersized, oversized, and not happy. You wasted dollars and wasted effort. So do a proper heat loss, heat gain, not that difficult to do. And backup heat is going to be required. And it can be electric, it can be hot water. If you even supplement with wood heating, that's fine too. So the heat pump does the majority of the heating, but the wood stove and the coldest of days can be useful. And just one last reminder, it's a refrigerant-based product. You need a qualified refrigeration technician to install and service these devices. And that's not necessarily a barrier, but something to think about who's going to help us with this. It's not a do-it-yourself type product. And Claude, those were the slides I had. I didn't ask you during the session, but I'll ask you now. What's been your experience? Any experience you've had with heat pumps, or more importantly, any questions that you think might be raised about heat pumps?
Gord, again, a great presentation. First off, in my, we'll call it former home inspection experience, heat pumps were, as indicated, probably not always good news for a home inspector to review, because I saw a lot of them that seemed to break down, say, roughly in a 10-year period.
Mm.
But, certainly the technology has changed. Certainly, like you said, the old saying used to be, well, they're really not designed for cold Canadian winters. Well, obviously, you've kind of turned that whole discussion right around, and I'm thinking right now, I'm getting close to thinking about replacing my forced air gas furnace. I'm thinking, you know what? I'm sold.
And
I'm sold because I think heat pump is the answer.
And I would say, John, even if you kept your gas furnace, but added a supplementary or I'll say an add-on heat pump, and we say to folks all the time, if you're replacing an air conditioner, don't replace your air conditioner with a heat pump. It gives you the air conditioning and gives you the option to run heat pump when it makes most sense. And there's, again, new thermostats that'll make those decisions for you. I will admit, though, I want to go back to your initial comment as a home inspector. It is a compressor-based system. There's no doubt about it. And compressors do fail over time. A good heat pump compressor should be minimum 12 to 15 years. If they're crapping out sooner than that, then I would say it was an improper piece of equipment, or it wasn't installed correctly, or wasn't serviced correctly. So compressor-based systems, new gas furnaces last about 15 years. New air source heat pumps last about 15 to 18 years, and they're entirely serviceable. That is, you can change out the compressor of a heat pump. And so we do need to acknowledge compressors in the past weren't particularly reliable, but these new variable compressors, much more reliable, longer life, just need to be properly sized, properly serviced.
Great. Again, I'm sold. You really clarified, and hopefully everybody gets the message here that, hey, that 300% really means a lot, especially to my pocketbook.
Absolutely. Well, thanks again for the opportunity. I always enjoy doing these with you, and I'm sorry I couldn't do it live in this session. We'll get back to doing those shortly.
Again, thank you very much, Gord. Very much appreciated. And certainly I've always enjoyed the building knowledge, just looking on your website and looking at all the great information that's available out there.
Well, thank you for that. And I would encourage folks, buildingknowledge.ca or constructioninstruction.com, two really good websites with good building science information. We're always happy to help if you have any questions.
Thanks again.
Thank you. Bye now.